Okay, let's talk about let's finish this phase shift in RC circuit. Okay, you're talking about last time. Okay, so the different frequencies values. Okay, XC basically it varies. Okay, when XC varies, so the value of theta, since it depends upon XC1, okay, it would vary. So we last time we said that when frequencies are high it is 0, and for cutoff frequency is 45, and when further reduction in the frequency it comes out to be 84.3. So so if I'm okay, this was the board plot. Okay, this is frequency. So FC, okay, over here your phase is 45 degrees. Okay, but anyhow, what can I do over here? It's better to find this is over here. So if I plot, okay, frequency, okay, with respect to frequency versus the calculated theta values. Okay, so when something is, okay, increased beyond FC, so we just talk about that if FC is our reference frequency. So anything if frequency is increased, okay, above FC, so theta tends to be 0. So theta tends to be 0. So if this is theta, this is the x-axis, it tends to be 0. Okay, and at FC it is 45, and at FC it is 45, so it is done, right? And then at a reduction in FC, so if frequency is reduced, okay, further down FC, okay, if frequency reduce, okay, from FC, so basically there is a gain which is 84 point, and it occurs at a frequency of 0.1 FC, 0.1 FC, when this much, this for lower frequency of value this much. So this is 84.84, 84.3, and then it means that if I further decrease the value of this frequency, okay, so it means that this phase shift can be increased. So this phase shift will go to 90. So it means that, and this is positive, so we prove that the phase shift introduced is a leading phase shift, and we can write, or if you plot the plot, okay, VB, this is V in, okay, this is your V in. So if a signal is coming, okay, towards the amplifier, okay, because of the RC, okay, it would be affected by, it would be offered by some phase shift, and we, okay, so at the base, okay, now VB, this is the voltage at the base, okay, the phase shift it occurs, and this is, okay, and this is a leading phase shift, so that's why VB is leading V in. We can see VB, this is leading then V in, so that's why the result is the voltage at the base transistor leads the input voltage, okay, and so this is the net conclusion. Now this is, okay, this is the effect of low frequency response on amplifier, okay, at the input. Remember, at the input. Now similarly you can calculate, or you can estimate the low frequency response at the output. So at output we have another RC circuit which is at the emitter, okay, with another RC circuit which is at the coupling at the collector side, okay. So this is how we can do the analysis for the rest of the inputs, RC circuits, but for input circuit we completed that. Now the next thing, we jump into another important thing, that high frequency amplifier response. What would happen that if I increase the operating frequency? If the operating frequency over here, if it increases, so remember this XC, this was equal to 1 by 2 pi FC, 2 pi, okay, 2 pi FC. So if this increases, this frequency increases, so this would decrease. So if this decreases, so it means that C1 XC, okay, I can assume this to be, if it decreases, so I can assume this is to be 0, this to be 0, okay, this xc again it can be 0, and this can be 0. So this is the case become very ideal case as we study in chapter 5, 6 and 7. Okay, but because of this reactance, when it becomes, we treated this reactance is 0, but the problem is that the high frequency there will be a formation of internal capacitances, okay, which have a significant effect on the gain. So what would happen, that an internal junction capacitance between the collector and the base would form, okay, over here, and then between the emitter and the base would form, which is over here. Now, okay, at high frequencies, okay, and this occurs at only at high frequency. For low frequencies, okay, these are open, this we can assume this to be open circuit, but at high frequencies now this effect comes into play, we cannot ignore it, so we have to study this effect of these capacitances. So Miller theorem basically it solves this particular case, this particular scenario. So it says, the Miller theorem says that if you have a capacitor from the output to the input, okay, so it say that you can replace this capacitor at the input side by C in, okay, and similarly the effect of this capacitor is also on the output, so you can replace this CB by C out Miller. So the statement says that the Miller capacitance, okay, for CBC, we talk about CBC, and CBC is why, because from the output to the input, remember the CBE is different, it is in the input, already in the input loop, okay, so you can this is already taken into account in the input, but this C in the CBC, which is the capacitance from the output to the input, by Miller theorem says that you can replace, okay, when you remove this one, so to remove this one you should place a capacitor in the input side, okay, over here, and also, okay, a capacitor, okay, this is ground, remember this is ground, also a capacitor at the output, okay, in the output circuit, a capacitor, this is capacitor, another capacitor in the output circuit. This capacitor is known as similar, which is given by CBC, okay, gain plus 1, no need to derive this equation, and this is C out, which is given by, again, by this equation, no need to derive this. So the equivalent circuit I can construct is that, okay, R1 and R2 in the same place, RS in the same place, this capacitor, okay, is replaced by this one and this in the output, so I can replace this over here and over here. CB is the same, and this, so this is the equivalent high frequency circuit for the transistor. Okay, thank you.